Hello and welcome back to the Hyperthesis episode 46. Well, it's good to be back. My name is Pheely.
I'm Patrick.
And I'm Liam.
Well, this week we welcome Liam back from his exodus to Italy and won some award too, I believe. He's being, a great scientist, great young scientist in Italy. So I think Liam going to be talking a little bit about that, and let's see how it goes.
Yeah, I'll come back to that. Just want to apologize for this episode being delayed because I was flying for a very long time. I think I was traveling for like 42 hours straight on the weekend, which was not a great time, but I made it. Here we are.
Happy to have you.
Yes, thank you. I was glad to be sleeping in my bed last night. So yeah, what did I do? So yeah, I went to Italy, to a place called Trento, which is one letter off from where I grew up in Trenton, Nova Scotia. So that's something. But I went to this conference, and it was hosted by the European Centre for Theoretical Studies and Nuclear Physics in Related Areas. But that's a very long title, so they call it ECT STAR, where ECT is the European Centre for Theoretical, and then the STAR is just whatever they study, everything. It's a very physicist thing to do, isn't it?
It's like in computer science, you use like wildcard, right? Stars or sometimes like question mark. It's really funny. At least they don't use something weird like underscore.
Yeah, ECT underscore and then whatever. ECT STAR in Trento, Italy. And the conference was titled Quantum Simulation of Gravitational Problems on Condensed Matter Analog Models. So basically, it's this analog gravity stuff I study. It's these systems that you can make in like a fluid or a condensed or like a solid state system, and they mimic aspects of gravitational physics. You basically tune your system so that your equations are the same in some regime, and then you can see what happens. Because it turns out, if you want to study things like black holes and the formation of our universe, well, they're very far away, black holes, and we can't really study them up close. We can't poke them with a stick and see what happens. And also, for the universe, we have a sample size of 1, and we cannot go back in time to when it formed. So, like we always talk about, if you're doing, if you're doing physics, you need to be able to do an experiment to prove it, and it's not really physics if you can't experiment on it. So that's what this conference is about. So it was really cool because it was about 40 to 60 people. It's a small kind of niche community, and that wasn't everyone, but a lot of the really, really big names in my field were there for both these experimental and theoretical, both experimental and theoretical stuff. So it's very cool and humbling to be there.
So are there any string theories or zero? Because, it has to be testable, right?
Yes. Some of the people there know about string theory a little bit, but I wouldn't say they're string theorists. It's interesting because, so when it comes to gravity, people, they treat Lorentz invariance. So basically saying that things can move at the speed of light, which comes from, it's very important in relativity because you have all these symmetries and you really want them to be obeyed. But it turns out, Lorentz invariant gravity doesn't get the full picture. So whenever you try and study Lorentz violating gravity, many of these, string theorists and these quantum gravity guys, they just refuse to even acknowledge that it's a possibility. Whereas there are a lot of people who study this, like even the gravity people, they study these Lorentz violating theories of quantum gravity. And we've talked about it a little before, but it's very hard to convince many people that this is worth studying. And because these analog models aren't technically, they're not these real relativistic models, many of the quantum gravity people just don't care about them and they kind of refuse to acknowledge them. Whereas the ultra cold people, the people who study ultra cold atomic physics, they see this and they're a lot more receptive to the idea of it than the really hardcore string theory guys are. So in this community there's a lot more kind of realistic, down to earth people than there are these cosmologists. Although the cosmologists are getting more and more into it over time because I think they're starting to realize the value in these analog models. There's a quote by James Clerk Maxwell, who's famous for his electromagnetic equations, and it's that the recognition of the formal analogy between two systems leads to a knowledge of both more profound. Oh, sorry, let me say that again. The recognition of the formal analogy between two systems leads to a knowledge of both, more profound than could be obtained by studying each system separately. I think when I wrote this down, I put a comma in there for some reason. There's not supposed to be, but you get what I meant. So after attending this conference, it was very evident to me that this is true.
Well, we do it all the time, right? To further the understanding, because let's say you're investigating something, first thing you do, well, kind of, is like literature review, right? Like, or draw analogies to the systems you know. If you want to study, I don't know, black holes, you might want to see what's similar to the black holes, and maybe this behavior that's are um analogous. Like for example, like black body radiation, right? We know black holes emit some black body radiation, but to further understand black body radiation, we actually look at auto material. Let's say how iron turns red when it's hot, or auto material how when it heats up and emit different wavelengths of light. So by well drawing some correlation between like sometimes very distinct systems. Sometimes they have like certain attributes or properties that are common that we can use to define a theory, like black body radiation, or mass, like understanding how gravity works in the different situation.
Yeah, there's this actual. So one of the big topics of the conference was how there's this thing called emergent gravity. Um, and I don't quite know how to describe it simply, so I'll wing it and see what happens. But essentially, it's the idea that what we see as gravity, so general relativity, is just some kind of mean field theory of a true theory of quantum gravity. So the idea is that it's like in these Bose-Einstein condensates, there are these ultra cold quantum gases that display macroscopic quantum behavior. Um, but you can kind of approximate it with fluid mechanics. And that's kind of the similar. So you need quantum mechanics to describe it, but you can make a kind of like hydrodynamical approximation to them and treat them as some kind of fluid with some quantum corrections or things like that. And that's kind of the same idea. This idea of emergent gravity. I explained it very badly, but I'll do an episode on it in the future probably because I'm starting to gain interest in it. But basically, there's like a really close analogy between Bose-Einstein condensation and this emergent quantum gravity. It's kind of like you're treating gravity like a BEC, which is something I'm very interested in. It's there's more to it than that, but that's the idea. Like mathematically, that's what you're doing.
Like, what do you mean, like somehow like some graviton share ground states, or
No, no. I better not talk about it anymore. I'm not doing it any justice. I want to do an episode on it, but it's very nice because the whole point is that there's a really good analogy between these analog systems people are studying and gravity. It seems so it's worth studying in more detail.
Yeah, I mean the condensation criteria for BEC there is very specific, right? To me, it's like it's pretty unique. Well, maybe that's why it's called BEC. It has a
Yeah.
very
Well,
great name for it.
mathematically, what you do is you treat your ground state as a mean field. So you replace, for the physicist, you replace a field operator with a function. And in emergent gravity, that's what you do. You replace kind of this quantum field with a function, and then general relativity comes out of that. So that's the idea for people who know about quantum field theory. But so these analog, yeah, it was really cool to be at this conference anyway with all these people I've been citing and like reading their papers for years, and talking to them and having a drink with them and having like conversations about my cat with them or bagpipes or things like, just random, just seeing them be people since they've been just names on papers for me my whole life so far. And there's all these different kinds of analog systems people are studying. So they're studying things that mimic black holes, Hawking radiation, which is like mostly what I talk about when I talk about analog gravity. But there's a lot of people mimicking like inflationary theories of the universe and the nature of the vacuum of space and what the inside of neutron stars might look like, and analog to condensed matter systems, and even things like quantum chromodynamics. There's this thing called lattice quantum chromodynamics, which I don't know a lot about, but people are studying it. Particle production and things like that. And also, a big and upcoming thing in this field is entanglement in quantum computing. So people are kind of making like analog systems where they can study what entanglement and things like that, and how that could be used in quantum computing.
How do you create like an analogous entanglement? Well, I guess you can try
Well,
to do it in a computer, like make rules, for so it work that way. But like, you can't entangle sound wave, right? Like,
yeah,
can
yeah,
you?
yeah, it's a thing. I don't know. I This is something I don't study, but a lot of the conference was talking about how you can create analog systems where you have like phonons and look at their entanglement, or even you can create analog systems in fiber optical cables. So you can get photons and you can have them entangled and things like that.
Well, phonon entanglement. That I'm quite skeptical about that. It's strange.
Well, I mean, I don't know the details. I have to read up on it. I've never studied this stuff, but like people talked about it, so I was gonna blindly trust them.
I will just say I do remember vaguely reading a couple things about photon phonon entanglement.
Well, like
And we may have,
these
but
they're
phonon.
phonons. They're phonons, but they're phonons in a quantum gas. They're not phonons in the air, right? So maybe there's something going on there, but I don't remember the details honestly. I don't want to talk about something that am not able to meaningfully do justice. I don't want to say anything too wrong, but you can calculate. That's how they um experimentally verify the Hawking effect. It's all done with correlation functions, which is just another way to calculate entanglement. And what you find is these two phonons travel away from the horizon and they're correlated.
Well, what else did you do in Italy? Sightseeing wise, like have you go seen any major attraction or historical place, or have you eaten any good Italian food? Maybe some mozzarella, or maybe I don't know, pasta, pizza.
I just want to say one last thing about these analog things. I just want to say some of the systems they were studying were very cool. So like I said, you get BECs, these Bose-Einstein condensates, which I mean, listen to the first episode we've ever produced if you're more interested in that, because that was about those a little bit. Um, but yeah, and these optical systems, you can get them. You create these analog systems with water waves and with vortices, or in water wave tanks, where you don't have spontaneous Hawking radiation, you have like stimulated Hawking radiation. Superfluid helium, or there was a really cool one where they were actually doing it in literal air, which is something that I didn't even realize could be done. The way they did it was very clever. I'm not even sure. I don't remember the details, but it was very interesting how they did it in air. Because turns out air is a very complicated thing when you try and flow it. You get turbulence and dissipation and all these weird effects that are hard to deal with. So they had a very clever way to do that. Um, but yeah, so Italy. I didn't actually do many touristy things. I kind of just went straight to Trento, did the conference, and then left. But it was very fun. I ate so much good food. I pretty much just hung out in Trento and walked around and ate food and experienced the culture. It was very great. The food was so good. I must have gained like 30 pounds. Holy. I had pizza and wine every day and gelata, and there was they fed us. The conference fed us very well. The Italians, they're very serious about their food, it turns out. Every meal was like a multiple course meal. even if it was just like a casual lunch, it was always like the appetizer and then the meal and then the second meal and then the dessert, and the whole time they're like pouring you wine and water, and oh my god, it was incredible.
Amazing. Um, Speaking of Italians, there's uh, I guess a facility under a mountain for particle physics that people in my lab and we did experiments with for my old dark matter research, but it was on the Italian-French border, and every morning they would arrive at the lab before starting any experiments or anything. They would go into the kitchen and start the pasta sauce first thing in the morning in this national, like world-renowned laboratory. They cooked first thing to make sure it was ready for
Yeah,
lunch.
they're so serious about food. It's inspiring. Like, also, Italy has this thing because I've never been to Italy, and I'm an ignorant North American. I don't really know what goes on anywhere until I go. They shut down Italy from like 12 to 3 p.m. every single day. Like all the stores close, everything closes. It's weird. I don't quite know why. I'm sure I could just Google it and it would tell me. But anyway, it was very interesting. And then they like going out like at nighttime. It's a very much you go out and eat at night and stay out late every night. So it was weird because it was like 11 till 11 p.m. every night. People are always out like on patios having drinks and food and stuff every single night. And I really like that actually. Kind of where I grew up, it's pretty much dead by 5 p.m. It's very sad.
Yeah, sounds like good lifestyle once, if you have money, right? Like if you get paid enough to be able to afford that. I know in Italy is still cost of living is still quite high, no?
Eating out didn't seem that expensive, honestly. Like it wasn't cheap, I'd say, but it wasn't ridiculous. So I go out and I basically buy like a full pizza and a glass of wine. It would be like 18 euros or something, which not bad. I get, doing it every single night would be a lot, but if you go out with like the whole idea I think is everyone goes out with their friends every night. So if you go out, split on a pizza and get a glass of wine every night, like that's doable, I think.
Anyway, we're going to
Oh, I'm not done yet, sir.
oh, well.
I just
Okay.
all right. Yeah, this thing Pheely brought up at the beginning about that award. So I don't like flaunting my own horn, but I want to talk about it because this conference was a weird one actually. It was very good. Um, but it was in honor of this guy, Renaud Parentani, who was a really big name in the field, who suddenly passed. He died in 2022 at the age of 62. And he was this really good physicist. I mean, my entire work is based on one of his papers. And he was very friendly, I guess, because everyone at this conference was really good friends with him or collaborated with him or had extreme respect for him. So it was actually really sad a lot of the time because you could tell he meant a lot to these people. It was very interesting being at this conference where it was in his honor. Like there was one of the days specifically dedicated to him, and people came up and talked about basically like their experiences with him and how he changed their career and all this stuff. But probably the proudest thing in my kind of physics career happened to me so far, which was in front of all of these famous people I'd been talking to and been citing, and like people like Bill Unruh, and um, he's the only one you guys might recognize, but there's a bunch of others that are kind of big in my field. Um, so myself, along with another person, a presenter, Anna Berti or Berti. I'm sorry, I'm not saying that right, probably, but we won this kind of inaugural Renaud Parentani Award for the best young scientist research presentations. And I was totally shocked because even in this niche field, like my research is kind of even more niche with this branch of mathematics catastrophe theory. And I don't even remember what like happened. I remember like they said my name and then I just like blinked and it was over. I was so in shock and kind of in disbelief that I got it. So it was a weirdly emotional moment for me actually because I don't know, it's this field of research I'm doing is so niche and it feels like no one ever cares about it ever. And I put a lot of effort into making this talk, like way more than I usually do. So it was really, really rewarding to kind of see these people take interest in it, even though I never thought they would. So I went for, and also the fact that this like award that was named after their really good friend, and it was the first time they've had it. They gave it to me, and they were all there, and it was weirdly emotional. So I went for a nice little philosophical walk, pondering through a garden afterwards on my own.
Well, well, congratulations, Liam. So if any of the audience want to congratulate Liam, you can just DM is what it's called, right? DM
Yeah.
the Instagram is page account. I don't use it, so anyway, some kind of message.
No, don't
That's
don't don't message me. Just go look up old
oh,
Renault
the
parent.
Hyperthesis
Yeah.
podcast, the Hyperthesis page.
Go look up Renault Parentani and have a read up on him. I know, again, I never knew him, but very influential in my field, and I think he deserved a lot more credit than he got.
I think that should be a wrap for the intro topic. So today, for the main topic, it's going to be one of the most important invention in a modern science or modern human history. I would say that the very thing we record these on, and everything we use electronically, almost everything, contain this essential invention, the transistor. And I think as physicists, our formative years, we had to learn about transistors, right? And I think for us, we learned with the engineers, and it was quite fun. But as a physicist, the way we look at transistors, we do care, I think, a little bit more about how it formed and what type of material, what type of semiconductor made this happen, rather than the practical side, like how to build gates or how to build a processor or electronic devices.
Yeah, gates and electronics, they're very complicated, and they're increasingly becoming more and more complicated as we advance our processing and manufacturing technologies. But in this case, I think we should go back in time a little bit and talk about the birth of transistors. What was there before transistors? Because computers have been around longer than transistors. But how did they work? And just to say, the inspiration for this topic comes from a sad event as well, the loss of another great person in science and also in industry, and that's Gordon Moore. So Gordon Moore was the person you may be familiar with. He came up with Moore's Law. So he was the founder of Intel. He did a lot of work with semiconductors and actually introducing them in these subsystems like circuit boards and all of that, integrated circuit boards. And he predicted that the number of transistors that can fit in the same area on a microchip will double every about 18 months to 24 months. That did change a couple times just as he actually saw its progression. But he passed away earlier this year on March 24th. And so I think it's a fun idea to talk about what came before transistors, why they're so neat, how they work from the physics side, like Pheely said, and how we can use them. So starting with before transistors even were a thing, we did have computers. You might be familiar with something like the Enigma machine, which was used in World War II to decode enemy Axis-powered messages that were encrypted. So it was essentially a very large, very powerful, very sophisticated encryption, hacking, or decoding device. But this didn't use transistors. They weren't around at the time. But a lot of these electronics use something known as vacuum tubes.
Yeah, it's kind of funny, isn't it? Like these, like very complicated at the time. It's still complicated as to like anybody who's like trying to build it. But if you compare the processing power that if you want to decrypt that these days, it probably take like microsecond or something, some that's ridiculous if you write everything in like high assembly that because we have like gigahertz of of speed, right, in our processor, and to beat the Enigma machine now is like you clearly press a button and it's done. Back then, it actually takes like hours. to be able to find a decryption key.
I did we talk about encryption before with like prime numbers and things like that? I feel like we did.
I think we may have, and we also talked about Alan Turing himself. So I think
Yeah.
we did a little bit about that.
Very interesting stuff. For the Enigma machine, I'm very ignorant on this topic. My head's in the black hole clouds or whatever, but did they use prime numbers and stuff like that for the Enigma machine?
Like the machine.
I don't know how it worked at all. There's a movie. I should probably watch it, right?
So the Enigma machine itself was what was used by the Nazis to create these messages, and it
Oh,
was actually
right.
all. I believe it was almost all analog, if not completely analog.
Yeah.
So it had these different ciphers inside that changed constantly and depended on a whole bunch of things. And so it was actually, I believe it was the Bomba, which was the computer that was actually used to break the Enigma code. So these Enigma machines were produced, creating these codes, and it took this Bomba computer to actually break that code from, again, what I believe is an analog machine, but I might be mistaken with that.
Different than the analog I was talking about earlier as well.
Yeah, analog in this case means no electricity needed. It's all mechanical. But yeah, this very complex machine, like you said, could be replicated easily in a computer, very hard to build, and even harder nowadays to build because of the fact that we don't really have vacuum tubes. They are still made in some scenarios, I believe, but it's very hard to find them. A lot of devices do not use them anymore, but they were very common in most electronics for quite a while.
Well, yeah, I think vacuum tubes. I think when we grew up, we saw some of those machines, right? Like especially from like TVs and stuff. But back to transistor, I think it's such an interesting thing because to me, like diodes and transistor are very similar in terms of their makeup, right? Like, oh, well, they are both created from transistors, where, well, not from transistor, from semiconductors, and the fact that the transistor can act as a gate. Well, gates mean like it blocks certain things. Once there's a threshold that the signal reach, and then the signal can go the other way. It's like a junction, right? So that is such an, let's go, creative way to put in these semiconductor in that, the invention of, well, the inventor transistor must, you know it I don't know if they realize the potential of what transistors could be, but if they see it now, it's such a completely different what's it called, scope, I believe, than what they when they started inventing it.
Yeah, well, like the first gates, like logic gates and things, they were made with like water flowing in pipes and weird things like that, which I don't know a lot about. I've just heard of this. But the first transistors were made with vacuum tubes. So how does like what is a vacuum tube? It's a tube of vacuum, but how do you make a transistor with one of those? And what does a transistor, like you said, it kind of acts like a gate in some ways, but what does it do?
So just to clarify, transistors are, I believe, defined as semiconductors. So you need semiconductor material to be a transistor. But prior to transistors being invented, which I think we're going to hear a bit more about in our story, vacuum tubes essentially did the exact same thing. So you had this something that looked like a light bulb. So it was this vacuum tube with a filament and then a plate. And essentially what would happen is that there was a high voltage that could be held across the plate and the filament. So the filament would produce a high voltage, it would go to the plate, creating a complete circuit. However, there is a slight bias in that so that the voltage wasn't able to actually jump. So you had this third entry point for some sort of electrical signal to come in. And when that third entry point was triggered, then you would see essentially an arc where the electrons are able to move from filament to plate, completing the circuit. And since it's a vacuum tube, these electrons are unimpeded and can move freely from one to the other directly because of the high voltage. However, you need that small little signal to say, okay, we're going to overcome this bias. and allow the signal to go through. If you don't have it, then there's no signal going to go through, no circuit is complete, and you don't have anything going through. So this is how a vacuum tube works. They're large. They were made out of glass to keep that vacuum. It's really cool because at one point you could just buy vacuum tubes and they would break occasionally or burn out, much like an incandescent light bulb, and you needed to replace them. So you could just buy them, slot them back in, it would all be good. But the idea of this small little bias being overcome by a small voltage, triggering a larger effect, is what helped inspire and lead to the creation of a transistor.
So yeah, transistors now, they're made with these semiconductors, which I guess if you think of a conductor like a metal, you imagine that it's this material, this crystal, I guess. So imagine it's like these tightly bound atoms that make up your solid, and then you get all these free electrons flowing around, and you can put in, like, for example, you can have a circuit with a battery, and then it causes these electrons to flow around in a circle through the metal. And so, but a semiconductor, I think, if I remember correctly, it's kind of like you have your metal, or I guess your semiconductor, and you have a very small amount of these freely flowing electrons or holes, or where a hole is kind of like the lack of an electron.
Yeah. So transistors are semiconductors such as silicon. That's by far the most popular one. So Silicon Valley, named after the fact that silicon makes up semiconductors. But this was actually first invented by the physicist Julius Edgar Lilienfeld, who filed a patent for transistors in Canada in 1925. So transistors are actually Canadian in invention. He contributed a lot of good stuff. But yeah, so they're semiconductors, just like the name imply. It is able to conduct electricity, but it's not great at it, but it's also not terrible at it. However, what we can do is we can add things to the silicon crystal structure to make it either more or less conductive.
Well, I think the point of using semiconductor is also its band gap, right? So I think we should start by explaining a little bit on how metal and insulators work. So usually an atom would have what is called the valence electrons, right? And for things to be conducting, that valence electron have to be in the conduction band, which is have higher energy. So for metals that are conducting, it's really easy to basically put the valence and the conduction band are really close, or sometimes almost the same, right? So it conducts electricity easily. However, insulators usually have really large gap between valence band and conduction band, that large energy gap. So it takes a lot of energy for that material to start conducting. However, semiconductor is quite an in between. Right? The band gap is not too large, but it's not too small either. So in a way, you can have a precise control as to when it should be conducting. How much energy should be applied before it starts conducting. And like Patrick said before, you can mix things. You can dope the semiconductor with other material or other elements to control that gap, to help basically design the gap to use as almost like a switch, but it's a strange switch where if you don't put enough energy or current through it won't start conducting. But if you put it for more than a certain threshold, it would start conducting really well. I think that was the point of semiconductor, if I'm not wrong. But yeah, I think that was how it worked in the easy explanation, right? But it's much more complicated to try to figure out the band gap for material. For example, there are good experiments that can be done to figure those things out, and theoretical foundations that you basically can calculate the predicted band gap.
Yeah, so it's worth talking about doping just a little bit. So doping is where you just put in a couple atoms within a group of silicon atoms of certain types of elements that are able to contribute or take away an electron from the overall electron cloud, if you will. So for the two different types of doping are N doping and P doping. So N being negative doping and P doping being positive doping. So these are done with two very common elements. It can be done with other elements, but essentially it's if that element has one more or one less valence electron than the material being used. So in this case, we'll use silicon as our example, since that's the most common semiconductor used. And for N doping, so you're adding a negative charge into it, you would add a phosphorus atom. So you just kind of sputter a phosphorus atom, make sure it gets within the lattice structure of the silicon, and that contributes an electron. So now you have a free electron just kind of hanging out there. And you tend to do this in a section of silicon. So if you have like a bar of silicon, you can dope half of it with phosphorus, which is N doping, and then you can P dope the other part, which is usually with boron, and that has one less atom. So one less electron. So since it has one less electron, there's essentially a hole, which Liam mentioned earlier, that's kind of positive since there's slightly less charge. And just between those two layers, so if you do half of your bar of silicon with phosphorus, the other half with boron, you're actually going to have a boundary layer where nothing really happens, and that kind of acts as a barrier between the two. So the positive side doesn't attract the electrons on the negative side, and they don't move. However, if you were to, say, apply a small voltage to this boundary area, things start happening. And it's because you're applying a very small voltage, you're removing that small boundary area, and then electrons are free to flow from the positive to the negative. No, from the negative to the positive, but the current flows from the positive to the negative. And so that's essentially how we get transistors, is through this doping and the creation of a slightly positive side and a slightly negative side, and then overcoming that boundary between them, we get transistors. And in that case, I believe it's called a bipolar transistor, where you only have those two distinct sides to it. Now, of course, we do have not just bipolar transistors anymore. We actually have many, many, many different types of transistors. But the first transistor that used this concept was known, and the main transistor still in use, is the field effect transistor. So the field effect transistor, or the FET, there were a lot of great puns made in our electronics course about Boba Fett and Jango Fett. But a lot of these different transistors are known as FETs, or field effect transistors. And that's actually what the original patent was applied for. Now, it was never actually put into practice until much later. But again, this was 1925 or 26. But the FET just kind of exploded in use once transistors were shown to work with proper doping and proper semiconductor use.
Yeah, and I think like for it, basically we can basically have our electrical switch that is controlled in a way like intrinsically by the material. I think transistors mainly are used as either a electrical switch or amplifier. So it depends on how you connect them, right? And what the type of transistor too. But you're gonna have like a little like tiny switch when we said gate, or for use for computers. This switch, if you can sequence them in a specific way, act similar to, you can store information, you can process information. That's why it's such an important piece of the computer.
Yeah, and I imagine you can do a bunch of other things with transistors by putting them in certain configurations with certain elements. I just Googled how many transistors are in a computer, and the answer was around somewhere between 500 million and 2 billion transistors in a modern CPU, because they can make them very tiny now, and it turns out they're very, very useful. So when we say, transistors are they're one of probably the most important inventions in electronics. You can see why.
Yeah, going back to Moore's law, So by the time the transistor was invented, it started to come around, and then it started to be actually produced. So again, Robert Moore was one of the founders of Intel, which I'm sure if you're listening to this, you most likely heard of. And so that first transistor that was produced was, I believe it was the Intel 4004, or right around that time. It was 1971, and that one had just a couple thousand transistors. And because of Moore's law, it says that the number of transistors on an integrated circuit will double approximately every 2 years, going up to today, where we're kind of reaching the limits of Moore's law. Just looking at a graph right now, we have 50 billion transistors on an AMD EPYC CPU, which is a very powerful one. And that's just crazy to think that we went from a couple thousand to tens of billions of transistors. And again, we are reaching limits because of quantum effects, which we might be able to discuss for a couple minutes. But overall, these transistors, these little doped pieces of silicon that are able to transfer larger amounts of electricity or electrons based on a small switch, are just so plentiful and so small now compared to the very first one, which you could probably hold in your hand. And now you can hold 50 billion in your hand.
Well, I think it's important to point out the being electrical switch, because before that, to think about what is a switch, right? Like, okay, because it's about like contact of the conductor material, right? Like, do you think of the old switch sign, or like in a diagram, a switch basically you break open the circuit, you basically disconnect part of the circuit, right? That's literally a switch, and people have done that by, well, literally disconnect part of the circuit, right? So like basically unwire certain things. That's like the old switch. But you don't want to have mechanical switch inside your processing unit where you have to like punch it every time or move it every time. So by having transistor as a electrical switch, which is like if I applied very small voltage, okay, the gate won't open, so the signal won't go through. Okay, then if I put enough voltage, then that gate open. So you can control things being open and closed using only electrical signal. Not, you don't need to use mechanicals. That's why I think it's so powerful that we're able to do this, and the fact that we can control 1 and 0 on and off. We can put multiple transistor together and then maybe make some kind of operations with binaries, right? Like let's say addition or well, I think almost everything is well, everything in computer is addition, even subtraction, right?
Yeah, and that's something also interesting about transistors is you can use a combination of them to develop gates, or logic gates as they're known. And so you can do these complex operations just from putting a couple of transistors in a certain orientation. And so these gates are used in computer logic all the time. You might use them when you're programming, but at the transistor level, they're also used, and that's what makes up the processors that are in your CPU, your GPU, whatever you may have. But these logic gates, a couple common ones are AND, OR, XOR, or XOR, depending on how you want to say it. But these are different ways in which we can combine signals and then get certain types of outputs. So we're now taking binary inputs and then putting them as binary outputs, but we can take multiple signals from multiple different transistors, put them all together, see what happens. And when you do this with a lot of different types of gates, say in an integrated circuit, then you can do complex math. So whether you're adding or subtracting, you're trying to work with these logic gates at the very base level. So everything that your computer is doing, or that you're listening to now, has to go through transistors at some point, and they're just doing very basic AND or other types of operations that have to do with these logic gates.
Right, because if you do that a billion times a second, like you can do a lot of things with it, right? Like, if you imagine if you have like a basket can compute a little bit, right? But it's really slow. Imagine having like billions of a baskets in series, or like not in series, connect in certain way, but like you can flick it really fast. So it's quite powerful. That's why we can calculate astronomical amount of data through it.
So something I'm really interested in is this quantum limit, this end of Moore's law. So it's something I've been. It's not just with transistors, but like other things too. Like if you the smaller and smaller you make them, eventually reach a point where quantum mechanics becomes involved and things get really hard and complicated. Um, for example, there's actually a field on quantum batteries trying to make batteries out of really tiny things, and I don't know a lot about it, but it's something I've read about every now and then in random physics articles. So how how does a transistor? I don't know what I'm trying to ask, but basically, how quantum?
Okay, how quantum,
Yes.
indeed. Um, so if you remember how we talked about if you have like this chunk of silicon, this plate of silicon, and then you dope half of it with one type of substance, if you N dope half of it, if you P dope the other half, you can get a signal across it. And that signal is carried because electrons are moving. Now, the smaller and smaller you go, the less space you have. And so when you have that boundary layer between the N and P doping, or however the transistor is arranged, there's somewhere it's N and then P and then N at the other end. But regardless of how it's arranged, as you get smaller and smaller, the electrons that are just kind of free within the semiconductor, the space that they're in becomes more restricted. And what happens if you have a limited potential and then an electron hanging out, and that potential is quite narrow, is you'll have quantum tunneling happening, where you'll have the electron has a probability of overcoming that potential since it's not an infinite potential, and it can actually cross that barrier. And so when it does that, the voltages that we're dealing with modern transistors are so small that that might actually be counted. So you might get a bit flip, which is a problem when you're trying to, say, store data or compute things, is if you have a bit flipped, it's now entering something wrong into the system and you're getting something incorrect that's being spit out. And so it's the effects of quantum tunneling, overcoming that potential essentially, that are causing these quantum limitations. Because of the behavior of electrons at very small scales, we are reaching our limits in size of semiconductors and how small we can go.
It's very cool how tunneling comes into these things. Quantum tunneling is a very interesting thing that we don't even understand very well, actually. Some of my there's some research I got, Josh, who was one of our guests, actually. One of his topic is related to the work of this guy, Ephraim Steinberg, I think, maybe from the University of Toronto. I might have gotten his name wrong. I think it's Ephraim Steinberg, but he's basically studying this thing called tunneling time, which is the idea that this particle tunnels from one side to the other with potential. I won't get into that, but there's other circuit components. I think there's actually like tunneling diodes where they actually use quantum tunneling as kind of. I remember in my second year electronics class, I took it before you guys did. I took it early with Heather, and Carl taught it, one of our old profs. I remember we had like a whole day where he taught everyone tunneling, which he did it for me and Heather because we were in second year and all the other people in the class were in fourth year. Um, but it came into play in one of these circuit things, and I can't remember if it was transistors or something else, but it's very cool how these quantum effects become relevant and how we're even able to get that close to this limit with billions of transistors in a computer.
I mean, since we are trying to get smaller and smaller, it's kind of natural that they're gonna reach the limit, which is gonna be a quantum thing, right? Imagine it's like you want to try to get make the biggest device ever, like biggest. What's the limit? Oh yeah, when gravity is becoming a problem, right? So I can see why, like, because of the scale they're trying to go through, that quantum effect's gonna become a problem. Which I don't know how people are gonna bypass it, but I don't know if we need to, because I don't think it's about the size of the transistor anymore. It's getting a
Maybe
little too ridiculous.
maybe you need them in quantum computing. I don't know, but what do you know what the smallest transistor that exists today is roughly? We can Google it, but I'm trying to imagine like I
Like
I have
nanometers.
I always, as a theorist, I always look at my theoretical limits, right? If I look at a transistor, I say, all right, what if I had a transistor made out of like not a couple, but like a few atoms? Could you even do that? If you have like 10 atoms as one material and you dope it with a single atom, like, is that possible? And of course, at that point, quantum effects are important, but I'm wondering, like, what's the smallest one you could make?
I know that like current processes for large scale production are at like the 7 nanometer or 5 nanometer level.
Wow.
And just looking very quickly at IEEE, it looks like the smallest transistor created as of March 2022 was 0.34 nanometers.
So that's like 10,
Tiny.
30 electrons, maybe. Or not electrons, atoms, right? Or I guess it
Yeah.
depends it depends what its dimensions are. I'm thinking in 1D, because of course I'm a theorist, but there's other dimensions too.
But that's something that companies are trying to do and researchers are trying to do is figure out ways in which we can pack more transistors into the same space. And it looks like that one 0.34 nanometer transistor, along with other larger companies like AMD and Intel and TSMC, who's ever producing these transistors, they're looking into actually stacking. So they're looking at the three-dimensionality of transistors. So instead of having a gate that's like 7 nanometers wide, they're looking at ones that are shallower, or I guess less wide, but taller. So they're able to stack things on top of each other, which is one way in which we're working on overcoming the limitations, but quantum computers, of course.
Yeah, one thing condensed matter people do a lot is you make everything 2D. 1D is really easy, but nothing is truly 1D. Everything's always 3D, even 2D things, but turns out a lot of the time you get really special kind of symmetries and effects when you flatten things to roughly 2D, so your math gets easier and your physics gets nicer a lot of the time.
There's a reason they want to do in 2D in the first place too. It's
Yeah,
like
yeah.
3D. How are you gonna distribute heat? How are you gonna cool that thing down, right? 2D, even 2D still have some problem, right? People put thermal paste on it and try to put a big heat sink sometime on the CPU and try to cool it down. But imagine 3D, how are you gonna cool like a middle of a cube, right? Then it have to be some kind of special cooling system that can handle that amount of heat. So we'll see what happens in the future.
I wonder if there's a way to like transfer its energy to some magnetic field or electric field or something. That would be kind of cool, actually, because that would go through all of it, presumably. Anyway, I like I like coming up with these weird little ideas which have no real basis, because I don't know this stuff very well. But
Also, just to note, these 3D, it's not like a cube transistor, but we're still dealing in nanometers off the board. So to the human eye, it would look flat, but to be able to fit these, they're stacking them in terms of nanometers. So I don't think cooling would be too much of an issue, just because we aren't having like cubic CPUs or GPUs, although that would be cool.
Well, I mean, Apple tried to solve this by when for the M1 or M2 like Pro Max thing, where you can connect two of the same processor together and use it, right? It's such an amazing thing too, right? It's basically two layered, but you just flatten them out. So
Apple's not the first to do it. But anyway, I guess wrapping up,
doing it
will
well
be
is
interesting.
different than doing it. So
They weren't the first to do it well.
they're the first to slap an Apple sticker on it.
There you go.
we'll see. I don't think they they're doing very well. I haven't seen any other competitors that do it better, so we'll see.
Anyway, it will be interesting to see the future of transistors and computing in general, especially with quantum computing becoming more and more prevalent. And if you are a specialist in quantum computing, we would love to have you on the show to talk about it and pick your brain and ask you a lot of questions. And that the same goes to anyone else. If you are an expert in your field or specialize in a certain topic, we would love to hear from you. It doesn't just have to be physics. It can be from whatever science field you enjoy, mathematics, which some people see as an art instead of a science. But whatever you want to talk about, feel free to contact us. There are many different ways to contact us, including our email. We're hyperthesispodcast@gmail.com. You can find us on Instagram at the Hyperthesis, where we post a lot of updates, such as this week's episode is a bit late. We posted an update on Instagram, so give us a follow, a like, and feel free to leave a comment or send us a DM to Liam for congratulating him, and also to us for if you like something, if you didn't like something, or if you want to talk about something. We are also on YouTube. You can like, comment, subscribe, do whatever you want on YouTube to our videos, and it's easier to share that way. And you can find our videos on pretty much every podcasting platform that exists. We are on Google Podcast, Apple Podcast, Audible, Amazon Music. We are based out of Spotify, so you can find us wherever you stream your podcasts. I will say we are no longer on Reddit. Our account got banned.
What?
So don't try and message us on Reddit.
Patrick, were you following some questionable subreddit?
Anyway, now is Pheely with the story, I believe.
Why did we get banned? I have the story, but why did we get banned?
Oh, you have the story. Okay, don't worry about it.
Was someone like Flat Earth commenting and you just fought them on it? I want to know.
We'll talk about it later.
This will be a secret that people will message us about. Anyway, so
yeah, message us to find out.
Yeah, okay, do that. Anyway, yeah, so my story today, it's kind of like a little, so the transistor, which we said was invented in 1947 by the three physicists, John Bardeen, Walter Breighton, and William Shockley at Bell Labs, and then it shared the 1956 Nobel Prize in Physics for their achievement, these guys. So today I'm just going to kind of give a quick little summary of each of them, and there's a lot of stuff I could talk about. All these people have a lot of things going on behind them, and they had lives and lots of stuff I could talk about, but I'm doing a quick little kind of version of this. So John Bardeen's probably kind of the most notable one, I'd say. He's the one that most people have heard of. He was born in Wisconsin in 1908 and died in 1991. He was an American physicist and engineer who was actually the only person to have been awarded the Nobel Prize in Physics twice, which is very interesting. He was awarded in 1956 for the transistor, like I said, but again in 1972, actually, along with Leon Cooper and John Robert Schrieffer for the fundamental theory of conventional superconductivity known as BCS theory. So BCS theory is this huge thing in solid state physics. People are trying to come up with room temperature superconductors, which is, I don't even know if we've talked about that. We really should if we haven't. But Bardeen, he graduated from high school in 1923 at the age of 15, and he actually could have graduated several years earlier, but didn't for various reasons. Some of them relate to his mother's death. So, like many of these famous physicists, he kind of puts all of us to shame, which is a little depressing, but here we are. Bardeen entered the University of Wisconsin in 1923, and while in college, he joined a fraternity and partially paid for his fees by playing billiards. So apparently he was a pretty good billiards player as well. He didn't actually want an academic life like his father. His father was the dean of the university's medical department, so he chose engineering because he felt engineering had good job prospects. He completed his Bachelor of Science in Electrical Engineering and also a Master of Science in Electrical Engineering, and then he worked as a geophysicist for a little while, but went on to get his PhD in mathematical physics from Princeton in 1936 under the supervision of Eugene Wigner, which is also a very big name in physics. Walter Breighton, the next guy, born in 1902, in Amoy, China, um, and died in 1987, was an American physicist at Bell Labs. He had American parents, although he was born in China. Um, his parents were a private school teacher for Chinese boys and a mathematician. And I think his father was actually the teacher and his mother was the mathematician, but I'm not quite sure. I got to double check that. Which is kind of the opposite of what you heard of for his time, which is very nice actually. But he earned his Bachelor of Science from Whitman College in 1924 with a double major in physics and mathematics. And he earned a Master in Arts from the University of Oregon in 1926, and then a PhD from the University of Minnesota in 1929. So these guys had all very different backgrounds, like real humans do. And he studied the new field of quantum mechanics a lot during his time. His PhD thesis, was titled "The Efficiency of Excitation by Electron Impact and Anomalous Scattering in Mercury Vapor," supervised by John Torrance Tate. I actually don't know who that is, but it was a physicist. And in August 1929, he began working at Bell Telephone Laboratories as a research physicist. In 1945, Bell Labs created a group specifically to do fundamental research in solid-state physics relating to communications technologies. And this is actually where the trio of Nobel Prize winners, Bardeen, Brayton, and the third one, William Shockley, were able to meet and produce a transistor. Even though you mentioned that a Canadian guy created the transistor much earlier, or he came up with the idea of it, I guess these three guys were the first to kind of make it efficient and make one that you can kind of mass produce, I guess.
Yeah, he patented it, but I don't think he ever made it.
Okay. So these were the first three people to come or make it realistic, I guess. Put it into the real world. So the final of the trio, William Shockley, was actually the manager of Bardeen and Brayton. He was kind of the group leader at this new Bell Lab group. He was born in 1910 and died in 1989, and he was an American inventor and physicist. Partly as a result of his attempts to commercialize the new transistor design in the 1950s and 60s, California's Silicon Valley actually kind of received its fame from that, and somewhat its title. So he earned his Bachelor of Science at Caltech and received a PhD from MIT in 1936, where the title of his thesis was Electronic Bands and Sodium Chloride, under the supervision of John Slater, which is another big name in physics. All these big names in physics, they're all supervised by other big names, which is very interesting. I don't know if that's the case nowadays, but definitely back then it seemed to be. And although Shockley helped create one of the most influential devices known to man, he actually went on to become widely known for his extremely racist views. So, as described by the Los Angeles Times, by his Los Angeles Times obituary, quote, "He went from being a physicist with impeccable academic credentials to an amateur geneticist, becoming a lightning rod whose views sparked campus demonstrations and a cascade of calamity." So, end quote. So he basically decided to switch fields, and he tried to use genetics arguments, something that he definitely wasn't an expert in at all. And he tried to argue basically that white people were superior to black people in terms of intelligence, and something about how, people are getting dumber because of people, getting married to whoever they want. So none of his arguments were actually supported by any by the scientific community at all, of course. And according to his biographer, who kind of studied him at one point, quote, "His racism destroyed his credibility. Almost no one wanted to be associated with him, and many of those who were willing did him more harm than good," end quote. So I just wanted to point this out because this is one of those very interesting situations where you have someone who was very good at physics or science, but they were kind of an awful person. Um, if you're interested, you can read up on it. It's a very interesting story. And it to me, it's just very fascinating how someone who's so scientifically oriented, when you do science, you can't have bias. You have to be very subjective. You have to look at the bigger picture. You have to keep in mind that the more you do something, the more bias you get towards it, and you learn to think a certain way. So you kind of always have to step back and kind of retrain yourself to not have bias and think differently. But it's very weird how like a physicist of all people, or an engineer, or a combination of both, was such a good scientist, but also they didn't apply any of that to their I guess moral beliefs, and it's just they had bad beliefs that were very not justified by the scientific method. So I just find that very strange and interesting. So yeah, he was a big shot, and then he kind of blew up in flames and went down the wrong path. But yeah, that's the story of these three guys. A very quick, short version of it.
All right, thank you, Liam, for the story. Yeah, it's quite interesting. That's why I adopt the principle of don't ever meet your heroes, because they are always up to a fault. Possibly my bias is up to a fault that they're always terrible people. But that's just my views about how I conduct my my business.
Yeah.
Anyways, thank you, Liam, for that story.
Nobody's perfect, but I mean, I hope my heroes aren't that bad.
Oh, don't meet them, and you keep that image, that beautiful, innocent image forever.
I feel like I'd rather know, but okay, fair enough.
All right, then I'll talk to you guys next week. Take care.
Bye, everyone.
Bye-bye.